Most people assume that every journey has an ending. A ship reaches a harbour. A plane lands on a runway. Even objects cast into space seem at first destined to arrive somewhere. We tend to think of motion as a temporary condition, a state between departure and arrival. But the universe does not always respect that intuition. In 1977, humanity launched a machine no larger than a small car. It carried instruments, computers, wires, golden records, and a faint ambition that reached far beyond its hardware. That machine was Voyager 2. At the time, it was built to study planets, moons, magnetic fields, and atmospheres. Its mission was expected to last a few years. Instead, nearly half a century later, it is still travelling. It has passed the giant worlds of the outer solar system. It has crossed the frontier where the influence of the sun begins to weaken. It now moves through interstellar space farther from Earth than almost any human-made object in existence. And yet this is only the beginning of its journey. That idea is difficult to absorb because human time and cosmic time barely overlap. 50 years feels long to us. 1,000 years feels historical. 1,000,000 years feels abstract. But the question before us stretches far beyond all of these scales. Where will Voyager 2 be in 1 trillion years? A trillion years is not merely a large number. It is a span so vast that nearly every familiar reference point begins to collapse. Continents shift, stars move, galaxies evolve. Entire civilizations, if they rise and fall, may do so countless times within such duration. Even more unsettling, the universe itself will not remain the universe we know today. By then, many stars that currently light the night sky will be gone. Entire stellar populations will have changed. The cosmic environment surrounding Voyager 2 may be almost unrecognizable. And this creates a strange paradox. Voyager 2 is tiny, fragile and finite. Its electronics are aging, its power supply is fading. Its instruments will eventually fall silent. From a technological perspective, it is temporary. But as a physical object, it may endure for periods vastly longer than human civilization has existed. Long after its final transmission. Long after the last signal reaches Earth. Long after the species that built it may be gone. The spacecraft itself may still remain, a silent artifact drifting through darkness. This forces us into a deeper question. When we ask where Voyager 2 will be, what exactly are we asking? Are we asking for coordinates, a nearby star, a location inside the galaxy, or something more difficult? Because in the deeper sense, location is not fixed in the cosmos. Nothing stays still. Stars orbit galactic centers. Galaxies move through clusters. Space itself changes over time. Even the emptiness between objects is dynamic. So a coordinate in today's sky becomes meaningless over sufficiently long timescales. This means our question contains a hidden assumption. We assume that space is like a map. Stable, static, predictable, but astronomy has slowly taught us something more subtle. Space behaves less like a map and more like an ocean. Not an ocean of water, but an ocean of motion. Currents of gravity, tides of stars, waves of radiation, invisible magnetic structures. Regions of density and emptiness constantly shaping trajectories. Objects do not simply travel through space. They travel through an evolving gravitational landscape. And Voyager 2, despite its small size, cannot escape that reality. At first glance, the spacecraft seems to be moving in a straight line away from the sun. That image feels intuitive. Launch, acceleration, escape, then endless drifting. But straight lines in space are rarely truly straight. Every star exerts gravity. Every gas cloud contributes mass. Every galactic structure bends paths even if only slightly. A tiny deviation today becomes a vast difference across millions, billions, or trillions of years. This is where our comfortable intuition begins to crack. Because if Voyager 2's future depends on countless gravitational influences across unimaginable spans of time, then perhaps no simple answer exists. Maybe there is no single destiny waiting for it. Maybe there are only probabilities, possible futures, possible encounters, possible endings, or perhaps no ending at all. There is another layer to this mystery. Voyager 2 carries something profoundly human. Attached to the spacecraft is the Voyager Golden Record, a golden phonograph record containing sounds and images from Earth. Greetings in many languages, music from multiple cultures, encoded fragments of a civilization hoping however faintly to be known. The record transformed the spacecraft into something larger than a probe. It became a message, not because anyone is likely to find it. The probability of interception is extraordinarily small. Instead, the record changed Voyager 2 symbolically. It turned the spacecraft into an emissary of a moment in planetary history, a physical memory of humanity, and memories become strange when placed on cosmic timescales. What happens to a message when the sender disappears? What happens to an artifact when the civilization that built it no longer exists? Can a machine become a fossil of intelligence? These questions move us beyond engineering and into something more philosophical. Voyager 2 is no longer just about propulsion electronics or orbital mechanics. It is about persistence, about time, about what survives. To understand where Voyager the second of may be in 1 trillion years, we must first understand where it truly is now. Not just its distance from Earth, not just its velocity, but its place within a hierarchy of scales: planetary, stellar, galactic, cosmic. Only then can we follow its path into the deep future. Only then can we begin to understand what forces will guide it, what dangers may await it, and what kind of universe will still exist around it. Because the greatest surprise may not be Voyager 2's destination. It may be the realization that the destination matters less than the changing universe through which it travels, and that raises the question that will guide everything that follows. If the spacecraft continues onward while the cosmos itself transforms around it, then after enough time has passed, will Voyager 2 still be traveling through our universe, or through something so changed that it would feel like another universe entirely? To understand where Voyager the second of may be in 1 trillion years, we need a place to begin that still feels familiar. That means returning home. Human beings evolved under the comforting illusion of stable skies. For most of history, the heavens appeared permanent. The sun rose, the stars returned each night. Constellations held their shapes across generations. The solar system felt orderly, almost architectural. Even after modern astronomy expanded our view, that intuition remained. We still tend to picture the solar system as a neat diagram from a textbook. The sun at the centre, planets orbiting in smooth ellipses, empty black space between them, each world moving predictably governed by elegant equations, first described by Isaac Newton and later refined by Albert Einstein. That picture's not wrong. It is simply incomplete. The solar system is not static. It is alive with motion at every scale. The Earth circles the Sun at nearly 30 kilometers per second. The Moon orbits Earth. Asteroids drift in resonant patterns. Comets fall inward from frozen reservoirs at the edge of solar influence. Even the Sun itself is moving, carrying the entire solar system around the galactic center at extraordinary speed. We rarely feel this motion because everything around us participates in it together. Stillness in astronomy is often an illusion created by shared velocity. Voyager 2 began within this moving system. It launched on August 20th, 1977 from Cape Canaveral Space Force Station aboard a Titan IIIe rocket. Although it bears the number 2, it actually launched before its sibling Voyager 1 due to the geometry of planetary alignment. That alignment was rare. Roughly once every 176 years, the giant outer planets align in a way that allows a spacecraft to visit multiple worlds using gravitational assists. Instead of carrying enormous amounts of fuel, a probe can borrow momentum from planets themselves. In simple terms, planets can act like moving slings. A spacecraft approaches a planet, falls into its gravitational field, curves around it, and exits with a changed velocity. The planet loses a tiny amount of orbital energy. The spacecraft gains speed. The effect is so small for the planet that it is immeasurable. For the spacecraft, it changes everything. Voyager 2 used this celestial choreography masterfully. It visited Jupiter in 1979, revealing volcanic eruptions on Io and complex storms in Jupiter's atmosphere. It reached Saturn in 1981, refining our understanding of its rings and moons. Then it continued onward to worlds no spacecraft had visited before. In 1986, it reached Uranus. In 1989, it passed Neptune. These encounters remain among the most extraordinary achievements in robotic exploration. Voyager 2 is still the only spacecraft ever to visit Uranus and Neptune. That fact alone says something profound about distance. Even with all modern advances, reaching the outer solar system remains extraordinarily difficult. After Neptune, Voyager 2 had effectively completed its original mission. Everything beyond that became an extended journey. But to understand what happened next, we need to appreciate scale in a more intuitive way. Suppose the Sun were reduced to the size of a grapefruit. On that scale, Earth would be a small grain of sand roughly 15 meters away. Jupiter would sit about 78 meters away. Neptune would be almost half a kilometer distant. Already the solar system begins to feel spacious. But here is where intuition fails. Even Neptune is nowhere near the true edge of solar influence. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies including Pluto. Far beyond that lies the hypothesized Oort cloud, a spherical shell of frozen objects, extending perhaps tens of thousands of astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun. The Oort cloud may extend 100,000 times that distance. On our grapefruit scale, the planets fit inside a neighborhood. The outer edge of solar gravitational influence stretches across continents. That is the scale Voyager 2 is entering. When people hear that Voyager 2 has left the solar system, they often picture it escaping into open, cosmic emptiness. But that phrasing is misleading. It has left the region dominated by solar wind. It has not fully escaped the Sun's gravity. Gravity weakens with distance, but it never truly becomes zero. Even now, the Sun still exerts influence on Voyager 2. The spacecraft remains in a very real sense tied to home. This is important because it changes how we think about departure. Voyager 2 is not a bullet fired into empty darkness. It is more like a drifting object gradually loosening from a gravitational web. Each year that web becomes weaker. Each year the surrounding galaxy matters slightly more. That transition is subtle. At first the Sun dominates everything. Later nearby stars contribute measurable influence. Eventually galactic gravity itself becomes the larger framework. This layered structure gives us our first major insight. Voyager 2's future cannot be understood solely through the solar system. The solar system is merely the first environment it passes through. Beyond it lies interstellar space. Beyond interstellar space lies the galaxy. Beyond the galaxy lies an even larger cosmic structure. And each layer introduces new forces, new timescales, and new uncertainties. Yet before we can explore those larger scales, we must confront a boundary once thought simple, but later revealed to be surprisingly complex. A frontier between the Sun and the galaxy. A border that is invisible, shifting and constantly reshaped by cosmic weather. Voyager 2 crossed that frontier, and what it found there challenged one of our most comfortable assumptions about where the solar system truly ends. For centuries, boundaries in astronomy seemed reassuringly clear. A planet had an orbit. A moon belonged to a planet. The solar system had planets, and beyond those planets lay the stars. The universe appeared to organize itself into distinct regions, each separated by understandable borders. Reality, as it often does, proved more subtle. Where exactly does the solar system end? At first, the question sounds straightforward. One might point to Neptune, the outermost major planet, and call that the edge. Others might extend the boundary to the Kuiper Belt, where icy worlds drift in darkness. Still others would choose the distant Oort cloud, where comets may remain loosely bound to the Sun for billions of years. All of those definitions are useful. None tells the whole story, because the solar system has more than one boundary. There is the gravitational boundary where the Sun's pull competes with neighbouring stars. There is the cometary boundary marked by frozen reservoirs of ancient debris. And there is another frontier, invisible but physically active, shaped not by gravity but by flowing particles. This is the frontier Voyager 2 approached. To understand it, we must first understand that the Sun does more than emit light. The Sun continuously releases a stream of charged particles, mostly protons and electrons, flowing outward in every direction. This outflow is known as the solar wind. Despite the name calling it wind can be misleading. Earthly wind is air moving through air. Solar wind is plasma moving through plasma, an electrically charged flow shaped by magnetic fields and solar activity. It travels astonishingly fast, often hundreds of kilometers per second. Near Earth we barely notice it because Earth possesses protection. Our planet's magnetic field deflects much of this charged flow, creating the magnetosphere, a protective bubble that shields life from constant bombardment. Without that protection, Earth's atmosphere would look very different. As the solar wind expands outward, it carries the Sun's magnetic influence with it. This creates a vast bubble surrounding the solar system. Astronomers call this bubble the heliosphere. For decades, many people imagined the heliosphere as a smooth sphere surrounding the Sun like an invisible shell. That image turned out to be too simple. The heliosphere is not rigid. It breathes. It expands and contracts with solar activity. It bends under pressure from the interstellar medium, the sparse gas and plasma filling the space between stars. It behaves less like a glass shell and more like a constantly shifting weather system. This matters because Voyager 2 is heading straight toward that frontier. As the spacecraft moved outward, instruments measured changes in particle density, magnetic fields, and radiation levels. Scientists expected transitions, but the exact nature of those transitions remained uncertain. The first major boundary Voyager encountered was the termination shock. This is the region where the solar wind racing outward at supersonic speeds begins to slow dramatically as it collides with pressure from interstellar material. The term shock may sound violent, but in space this is not an explosion. It is more like a traffic jam in plasma. Particles that once moved freely begin piling into slower, denser flow. Voyager 2 crossed the termination shock in 2007. That crossing alone revealed something surprising. The heliosphere was asymmetrical. If the solar system were perfectly balanced, the shock would appear at roughly equal distances in every direction. It did not. The Sun's protective bubble was distorted. Something outside was pressing unevenly against it. That something involved interstellar magnetic fields and the surrounding galactic environment. Even here, far beyond the planets, the galaxy was already pushing back. After crossing the termination shock, Voyager 2 entered a region called the heliosheath. This was the outer layer of the heliosphere. Here the solar wind had slowed, compressed, and become turbulent. If the inner solar system feels orderly, the heliosheath felt messy. Particle flows became more complex. Magnetic interactions became less predictable. The boundary ahead was near, but still elusive. Scientists watched carefully. Then came one of the most important moments in the mission. On November 5, 2018, Voyager 2 crossed the heliopause. The heliopause is often described as the boundary between the heliosphere and interstellar space. This was the moment the outward pressure of solar wind could no longer dominate the surrounding medium. In simple terms, Voyager 2 had entered the space between stars. That statement sounds clean. The reality was not. Because crossing the heliopause did not look like passing through a wall. There was no dramatic line, no visible barrier, no sudden darkness. Instead, the evidence emerged through instruments. Solar wind particles dropped sharply. Galactic cosmic rays increased. Plasma density changed. Magnetic measurements shifted. The transition was real, but gradual and complex. This challenged another common assumption. We often imagine boundaries as lines. Nature often prefers gradients. The closer astronomy looks, the more boundaries blur. Coastlines become marshes. Atmospheres fade into vacuum. Galactic edges dissolve into halos. Even the frontier between our solar system and the galaxy resists simple definition. Voyager 2 taught us something quietly profound. The solar system does not end. It fades. That distinction matters. A sharp boundary gives certainty. A fading boundary introduces ambiguity. An ambiguity changes how we understand location. Where is Voyager 2 now? Inside the solar system. Outside it. Between categories. Depending on which definition we choose, all three answers can be defended. This may sound philosophical, but it has practical consequences. Because if the solar system's edge is diffuse rather than fixed, then Voyager's transition into the galaxy is not a single event. It is an ongoing process. Every kilometre outwards shifts the balance. The sun matters slightly less. Interstellar space matters slightly more. This gradual handoff reveals the deeper truth. Voyager 2 is no longer primarily a planetary mission. It has become an interstellar observatory, and the data it sends back is extraordinary precisely because humans cannot yet travel there ourselves. Even our fastest future spacecraft concepts would struggle to reach these distances quickly. So Voyager gives us something rare, direct measurements from a place once known only through theory, and those measurements brought another surprise. The interstellar medium was not the empty void many people expected. It contained structure, density, magnetic order, cosmic radiation. Even nothing had texture. That realization opens a new question. If the space between stars is not truly empty, then Voyager 2 is not drifting through a featureless vacuum. It is moving through an environment. A sparse one, yes, but still an environment capable of influencing motion erosion and long-term survival. Which means that crossing the heliopause was not the end of a story. It was the beginning of a new one. Voyager 2 had left the sun's protective bubble. Ahead lay the true interstellar dark, and what appears empty from a distance turns out on closer inspection to be filled with invisible structure waiting to shape the next chapter of its journey. By the time Voyager 2 entered interstellar space, it had already outlived nearly every expectation placed upon it. That fact becomes even more remarkable when we remember what Voyager 2 actually is. Not a futuristic machine built from exotic materials. Not an autonomous intelligence capable of self-repair. Not a vessel designed for immortality. Voyager 2 is in many ways a machine from another technological era. Its computer memory is measured not in gigabytes but in kilobytes. Its processors are unimaginably primitive by modern standards. Many devices now carried casually in pockets possess more computational power than the entire spacecraft. And yet Voyager 2 continues to function. That persistence is something important about engineering. Durability is not always about complexity. Sometimes it is about clarity of design. Voyager 2 was built during an era when reliability mattered more than elegance. Engineers at NASA and Jet Propulsion Laboratory knew the mission would travel where repairs were impossible. Every component had to survive vacuum radiation, thermal extremes, and decades of isolation. The spacecraft had to remain useful long after human hands could touch it. That requirement shaped everything. Voyager 2 carries scientific instruments mounted on a long boom to reduce interference from onboard electronics. It has communication systems aimed toward Earth. It uses thrusters for attitude control, gently rotating to keep its antenna aligned with home. That antenna is one of its defining features. The large dish nearly 4 meters across acts as Voyager's voice. Through it, signals travel across distances so immense that language begins to fail us. Radio waves move at the speed of light, roughly 300,000 kilometers per second. To human intuition, that sounds instantaneous. In the solar system, it is not. Today, a message from Voyager 2 takes many hours to reach Earth. This creates a strange relationship between humans and machine. Every command we send is delayed. Every response is delayed. Conversation becomes impossible. Communication becomes patience. When engineers transmit instructions, they wait and wait. Only later do they learn whether the spacecraft received, interpreted, and executed the command. There is something almost ceremonial about this exchange. A signal leaves Earth. It expands through darkness. Hours later, a machine built decades ago receives it. Then Voyager answers. A whisper crosses billions of kilometers back toward home. That whisper is extraordinarily faint. By the time Voyager's radio signal reaches Earth, its power is minuscule. Detecting it requires some of the most sensitive listening systems ever constructed, including the Deep Space Network, a global array of giant antennas in California, Spain, and Australia. The signal arriving from Voyager is often compared to detecting the power of a refrigerator bulb from planetary distances. Even that analogy understates the challenge. Noise is everywhere. Earth's own radio emissions, cosmic background interference, thermal fluctuations in electronics, Engineers must separate Voyager's signal from overwhelming noise with extraordinary care. This makes every surviving transmission feel remarkable. But no machine runs forever. Voyager 2's greatest long-term vulnerability is not collision radiation or structural failure. It is energy. The spacecraft is powered by radioisotope thermoelectric generators. These devices convert heat from the radioactive decay of plutonium into electricity. They contain no moving parts, which makes them exceptionally reliable. But radioactive decay is unavoidable. Over time, power output decreases. Slowly, steadily, irreversibly. That decline has defined Voyager's modern mission. As available power drops, engineers must make difficult choices. Which instruments stay on? Which systems shut down? Which scientific capabilities are worth preserving longest? Each shutdown extends mission life but reduces observational capability. The spacecraft becomes quieter not only in signal strength but in function. One by one its sensors fade. This process carries emotional weight because it mirrors something familiar: aging. Not in a biological sense, but in an operational one. Voyager 2 does not suddenly fail. It gradually loses abilities. First one system, then another. Function narrows. Purpose concentrates. Silence approaches incrementally. And yet even when power ends, the spacecraft itself will not vanish. This distinction is central to our journey. There are two different endings for Voyager 2. The first is communicative death. This occurs when it can no longer send usable data to Earth. That moment is approaching within decades. The second is physical destruction. That may not occur for unimaginably longer. Long after Voyager stops speaking, it will still exist. Metal structures, wiring, fuel residues, the Golden Record. Its body will continue moving through space. This is easy to overlook because humans often equate silence with absence. We assume that what no longer communicates is gone. Astronomy teaches otherwise. Many things remain long after they stop emitting signals. Dead stars become white dwarfs. Collapsed stars become neutron stars. Even black holes can persist for durations that dwarf stellar lifetimes. Silence does not mean disappearance. In Voyager's case, silence simply marks a transition. From active spacecraft to cosmic artifact. This transformation changes how we should think about its future. While operational Voyager's path matters partly because of science. After silence, its path becomes something else. A question of celestial mechanics, material survival, deep time. Once communication ends, Voyager ceases to be an instrument and becomes an object governed almost entirely by physics. No more course corrections. No active decisions. No intervention from Earth. Its future becomes passive but no less fascinating. And there is another reason the spacecraft matters. Voyager 2 carries human intent frozen in hardware. Every bolt placement, every circuit choice, every etched instruction. The spacecraft reflects a civilization at a specific technological moment. Late 20th century humanity built this machine without knowing whether it would outlast its creators. That uncertainty gives Voyager unusual symbolic power. It may become one of the longest surviving artifacts of human civilization. Not because it is indestructible, but because space is paradoxically gentle. We think of space as hostile, and for life it often is. But for inactive metal objects, the absence of atmosphere changes everything. No oxygen means no rust. No rain means no erosion. No biological decay. No weather. Damage still happens through radiation dust impacts and particle erosion, but these processes can be extraordinarily slow. In deep space, destruction often requires patience measured in millions or billions of years. That brings us to an unsettling realization. Voyager the 2nd of May survived longer than monuments on Earth. Longer than cities. Longer than nations. Potentially longer than our species. A machine designed for planetary exploration may become one of humanity's most durable relics. But durability alone does not determine destiny. Survival is one question. Trajectory is another. Voyager 2 still moves, at remarkable speed. And although it feels free, that freedom is incomplete, because even silent objects remain subject to one universal force: gravity, invisible, relentless, patient beyond comprehension, and over immense timescales, gravity ensures that no journey through the galaxy remains perfectly straight. When we think about emptiness, we often think in absolutes. Empty means nothing. No matter, no structure, no influence. Space at first glance appears to justify that intuition. Between stars lies darkness so vast that even light needs years to cross it. Against such scales, matter seems rare, almost accidental. But astronomy has repeatedly shown that emptiness is rarely empty. The interstellar space through which Voyager 2 now travels is sparse beyond everyday comprehension, yet it is not a vacuum in the absolute sense. Even here, atoms drift, charged particles move, magnetic fields thread through enormous volumes. Radiation flows constantly from distant stars, stellar remnants, and ancient cosmic events. Space contains almost nothing. Almost. That final word matters. Because over short timescales, tiny influences seem negligible. Over cosmic timescales, they accumulate. To appreciate the scale of Voyager 2's surroundings, consider the density of the interstellar medium near our solar system. On average, there may be roughly 1 atom per cubic centimetre, though the number varies greatly depending on region. 1 atom in a volume smaller than a sugar cube. Compared with Earth's atmosphere, this is extraordinarily thin. Sea level air contains around 10 quintillion molecules in the same volume. The contrast is difficult to visualize. Interstellar space is far emptier than the best vacuum chambers humans can build. And yet that sparse medium still matters. Voyager 2 is moving through it at roughly 15 kilometers per second relative to the Sun. That speed feels enormous by human standards. It would carry a passenger from Hanoi to Ho Chi Minh City in well under 2 minutes. But the galaxy uses different scales. At interstellar distances, even this speed feels modest. The nearest star system, Alpha Centauri, lies over 4 light-years away. If Voyager 2 were headed directly toward it, which it is not, the trip would still take tens of thousands of years. That comparison changes our emotional sense of motion. Voyager is fast. Space is incomprehensibly larger. This is why interstellar travel remains one of the most difficult challenges in science and engineering. Distance is not merely an obstacle, it reshapes meaning. A human lifespan becomes tiny compared with travel times. Civilizations may change before journeys finish. Even communication slows into patience. Still, emptiness does not imply irrelevance. Every particle Voyager encounters carries energy. Every dust grain matters. And while collisions are rare, they are not impossible. This introduces a subtle form of erosion. Not dramatic impacts. Not cinematic explosions. Microscopic wear. Tiny grains moving at high relative speed can strike surfaces and slowly damage exposed materials. Radiation can alter atomic structures. Ultraviolet exposure can weaken certain compounds. Charged particles can degrade electronics and surface coatings. For an operating spacecraft, these effects matter. For an inactive relic, they matter differently. The structure will not remain pristine forever. Over millions and billions of years, its surfaces will slowly change. Edges may pit. Coatings may erode. Fine details may soften. But the rate is astonishingly slow. In deep interstellar space, there is no rushing decay. Time itself becomes the dominant force. This reveals something strange about deep space. Near planets, matter shapes events. In interstellar space, scarcity makes time the greater actor. The environment does not destroy quickly. It waits, and waiting on cosmic scales is powerful. But particles and dust are only part of the story. The larger truth is that interstellar space has structure. Astronomers once imagined the regions between stars as mostly featureless. Modern observations reveal something far richer. The galaxy contains clouds of gas molecular regions where stars form hot ionized bubbles carved by supernovae and enormous magnetic structures stretching across light years. The Sun currently moves through a region called the local interstellar cloud itself, embedded within a larger cavity known as the local bubble, likely shaped by ancient supernova explosions. This means our solar system is not floating through generic space. It is moving through a specific galactic neighborhood shaped by long-forgotten stellar violence. Voyager 2 shares that neighborhood, and neighborhoods change. Over time, stars move, gas clouds drift. Shockwaves propagate, The medium surrounding Voyager in 1,000,000 years may be different from the medium surrounding it now. In 1,000,000,000 years, the difference could be profound. This introduces a new layer of complexity. Voyager is not moving through static emptiness. Both traveller and environment are moving. The spacecraft advances outward from the Sun. Meanwhile, the Milky Way itself rotates. Stars orbit the galactic centre. Spiral arms shift. Mass redistributes. Even large-scale magnetic structures evolve. The result is subtle but important. Voyager's journey is not like crossing a still desert. It is more like drifting through a vast, slowly shifting ocean. Currents exist. Density varies. Invisible structures influence motion and environment. And this raises a deeper question. If interstellar space has structure, could that structure meaningfully alter Voyager's path? Over years, almost certainly not. Over centuries, barely. Over millions of years, perhaps slightly. Over trillions. Now the question becomes unavoidable. Tiny forces integrated across enormous time can produce meaningful change. This principle appears everywhere in astronomy. Planetary orbits shift due to minute gravitational nudges. Asteroids become dangerous through subtle resonances. Galaxies reshape themselves through countless small interactions. Deep time amplifies small causes. Voyager 2 is subject to the same rule. Its current motion feels simple because we zoom in on short timescales. Extend the timeline far enough and simplicity dissolves. This is where our journey reaches its next turning point. We have learned that interstellar space is not empty. We have learned that Voyager is durable. We have learned that the environment around it has structure. But none of these alone determines its ultimate future. One force matters more than all others. Not radiation. Not dust. Not material erosion. Gravity. Gravity is patient in a way few human concepts can capture. It does not need speed. It does not need contact. It acts continuously silently across distance. And over millions, billions, and trillions of years, gravity reshapes every trajectory. Even those that appear straight. Especially those that appear straight. Which means that to understand where Voyager the 2nd of May eventually go, we must stop thinking only about empty space, and begin thinking about the invisible architecture underlying the galaxy itself. Because Voyager is not merely moving through darkness. It is moving through a gravitational landscape vast enough to bend destinies across cosmic time. Gravity is easy to underestimate, partly because it feels familiar. We live with it every moment. Objects fall, oceans rise and recede with tides, planets orbit stars. Because gravity surrounds us constantly, it rarely feels mysterious. Yet gravity is among the strangest forces in nature. Unlike contact forces, it requires no touch. Unlike light, it is invisible to human senses. It acts across enormous distances, shaping the architecture of the cosmos with quiet persistence. And most importantly for our journey, gravity never truly turns off. No matter how far Voyager 2 travels, gravity follows. Its influence weakens with distance, but never reaches absolute zero. This brings us to the first great question of our documentary. If gravity never stops acting, what does that mean for Voyager 2 over 1 trillion years? At first, the answer seems straightforward. Voyager 2 escaped the inner solar system. It is moving outward. Therefore, it should simply continue outward forever. That reasoning feels natural. It is also incomplete, because motion in the universe is rarely governed by a single gravitational source. Right now, the spacecraft still carries momentum inherited from launch planetary flybys and the motion of the solar system itself. That momentum gives it an escape trajectory relative to the Sun. In simple terms, Voyager 2 is no longer trapped in a closed solar orbit. It will not swing back toward the inner planets. That much is well understood. But escaping the Sun does not mean escaping gravity. It only means transitioning into a new gravitational regime. Think of gravity not as a single rope but as nested layers of influence. At the smallest familiar scale, Earth dominates nearby objects. At a larger scale, the Sun dominates planets, comets, and spacecraft. Beyond that, neighbouring stars contribute. Beyond stars, the mass distribution of the Milky Way becomes dominant. And beyond the galaxy, even larger structures matter. Voyager 2 is slowly climbing through these layers. That transition creates uncertainty because the future path of the spacecraft depends on more than current velocity. It depends on future encounters. Some will be weak. Some will be strong. Most will be subtle. But over sufficiently long time, scale subtle does not mean irrelevant. To see why, consider a billiard ball rolling across an enormous table. If nothing interferes, the ball travels in a straight line. Now introduce tiny slopes in the table almost too gentle to notice. At first the path barely changes. Given enough distance, however, the final destination becomes very different. Gravity acts like those slopes. Most of the time, Voyager 2 experiences no dramatic pull. Instead, it experiences countless gentle nudges. A nearby star passing several light years away. A dense molecular cloud exerting weak attraction. Galactic tidal forces altering motion slightly. Each effect is tiny. Each accumulates. This accumulation creates our first paradox. In the short term, Voyager's trajectory is highly predictable. In the very long term, prediction becomes increasingly uncertain. This is not because physics fails. It is because complex gravitational systems amplify tiny uncertainties. Astronomers call this sensitivity chaotic behavior. The word chaos can be misleading. It does not mean randomness. It means that small differences in initial conditions can produce large differences in later outcomes. A minute uncertainty in position today may become enormous over trillions of years. This makes forecasting Voyager's distant future fundamentally difficult. Even if we knew its position and velocity with extraordinary precision, future gravitational interactions remain impossible to predict perfectly. Why? Because the galaxy itself is changing. Stars move, new stars form, old stars die, binary systems interact, clusters dissolve, mass redistributes. The environment through which Voyager travels is dynamic. This leads to an uncomfortable realization. The question, where will Voyager 2 be in 1 trillion years, may not have a single answer. Instead, it may have many plausible answers, possible futures, probability branches, scenarios. That may sound unsatisfying, but uncertainty is not failure. In science, uncertainty often marks the frontier of honest understanding. We know enough to constrain possibilities. We do not know enough to declare certainty, and that distinction matters. Let us begin with what we do know. Voyager 2 is moving at roughly 15 kilometers per second relative to the Sun. That speed allows it to travel about 1 astronomical unit every 4 months, or roughly the Earth-Sun distance 3 times per year. Fast by human standards, slow by galactic ones. The Sun itself orbits the galactic center at around 220 kilometers per second. In other words, Voyager is not racing independently through the galaxy. It remains embedded within the broader motion of the solar system. This is easy to miss. We often picture Voyager leaving everything behind. In reality, the entire solar system is moving with it. The Sun, planets, comets, and Voyager all participate in galactic motion together. Voyager is separating from the Sun gradually, not instantaneously. This means nearby stellar encounters matter more over time. A star passing close enough could alter Voyager's path, not by capturing it easily, but by bending its trajectory. Even a small angular change today becomes enormous over millions of years, and over trillions, multiple encounters become nearly inevitable. This transforms our central mystery. The key question is no longer simply distance. It becomes interaction. What will Voyager encounter? Nothing significant. A nearby star, a dense gas cloud, a stellar remnant, something we have not yet considered. Every possibility changes the future. This is why astronomers often think statistically when projecting extreme timescales. Rather than predicting exact coordinates, they estimate likelihoods. How often do stars pass near one another? How dense is the stellar environment? How strong are typical perturbations? What kinds of encounters become probable over billions of years? These questions guide the evidence. And the evidence points toward a fascinating conclusion. Voyager 2's path will not remain isolated forever. Sooner or later, gravity from other stars will matter in meaningful ways. That realization opens the next phase of our journey. Because once nearby stars begin shaping Voyager's path, we must ask something far more concrete. Not just whether gravity bends the spacecraft's course, but whether one day, after ages beyond human imagination, Voyager 2 might actually pass close to another star. Perhaps close enough to enter another stellar neighborhood. Perhaps even close enough to cross the outer reaches of another planetary system. And if that is possible, then a once unthinkable question emerges. Could humanity's silent messenger someday drift past an alien sun? The possibility that Voyager 2 might one day pass near another star carries a powerful emotional weight. It feels almost poetic. A machine built by one civilization launched from one small world, eventually wandering into the neighborhood of another sun. But poetry is not prediction. Before considering such possibilities, we need to examine the evidence carefully. How often do stars actually come close to one another? The answer depends entirely on what we mean by close. Human intuition struggles here because the distances between stars are enormous. Even stars that appear adjacent in the night sky are often separated by many light years in three-dimensional space. Our nearest stellar neighbour Alpha Centauri lies about 4.37 light-years away. That sounds like a short astronomical distance, and relatively speaking it is. Yet even that nearby system is separated from us by roughly 41 trillion kilometres. In cosmic terms, stars are isolated islands. This isolation matters. If stars were densely packed, Voyager 2 would frequently experience close gravitational encounters. Instead, most of interstellar space is astonishingly empty. A useful analogy is to shrink stars down to grains of sand. On that scale, the average separation between neighbouring stars would still be measured in hundreds of kilometres. The galaxy is not crowded. It is sparse. That sparseness immediately lowers the probability of close encounters. Still, low probability does not mean impossible. Given enough time, rare events become expected events, and 1 trillion years provides extraordinary time. To estimate Voyager's future, astronomers model stellar motion using measured velocities and galactic dynamics. We can predict certain near-term encounters with reasonable confidence, at least on astronomical timescales. For example, Voyager 2 is expected to pass relatively near several stars over tens of thousands of years. One notable future encounter involves Ross 248, a red dwarf star moving through our galactic neighbourhood. Voyager the 2nd of May passed within a few light-years of such nearby stars over long periods. But this immediately raises a subtle point. Passing near a star in astronomy often still means several light-years away. That is not close in a planetary sense. It is barely close in a stellar sense. A spacecraft passing 3 light-years from a star has not entered that star's planetary system in any meaningful way. It has simply passed through the broader neighbourhood. This distinction matters because we are really asking two different questions. Could Voyager 2 pass near another star? Almost certainly yes, eventually. Could it pass close enough to encounter planets, comets, or debris belonging to that star? That is far less likely. Planetary systems are tiny compared with interstellar distances. Even large systems occupy only a minute fraction of the space surrounding a star. This makes direct interception extraordinarily improbable. To understand just how improbable, consider our own solar system. If another civilization launched a probe from thousands of light-years away and aimed randomly toward the Sun, the odds of that probe actually passing through the interplanetary region would be vanishingly small. Most trajectories would miss entirely. The Sun's gravitational domain is enormous compared with the planets, but the planets themselves occupy almost none of that volume. The same logic applies to Voyager. Even if it approaches another star, hitting a planet or crossing a dense inner system is unlikely. Yet unlikely is not impossible. And over sufficiently vast timescales, even extraordinary improbabilities deserve attention. This is where evidence becomes more interesting. Stars do not simply drift independently. They move through a galactic environment where encounters happen repeatedly across billions of years. The Milky Way contains hundreds of billions of stars, each following orbital paths shaped by galactic gravity. Those paths cross neighborhoods, spiral arms, stellar associations, and remnants of ancient clusters. The result is a constantly shifting stellar geography. The Sun itself does not remain among the same neighbors forever. Stars visible in today's sky are temporary companions. Over millions of years, constellations distort. Over tens of millions, the night sky becomes unrecognizable. Over billions, the solar system migrates through entirely different stellar environments. Voyager shares that migration. This is important because Voyager's future encounters depend not only on its motion, but also on the motion of every nearby star. Relative velocity determines encounter probability. A star moving in nearly the same galactic direction may remain distant for long periods. A star on a crossing trajectory may approach more closely. This creates a statistical landscape rather than a deterministic one. Astronomers often describe such problems using encounter rates. In the Sun's neighbourhood, stars pass within a few light-years of each other more often than most people realise. Close encounters on galactic timescales are normal. Extremely close encounters remain rare. This leads us to the evidence for gravitational perturbation. Suppose Voyager passes within a few light-years of a star. Would that star significantly alter its trajectory? Usually only modestly, but modest changes matter in deep time. A small deflection alters future encounters. Future encounters alter later ones. This creates branching trajectories. One gravitational nudge changes the probability of the next. Over millions and billions of years, these branches multiply. Eventually, prediction becomes less about path and more about distribution. We stop asking where exactly will Voyager be. We begin asking what range of futures becomes plausible. That change in perspective is subtle but profound. It transforms Voyager from a simple spacecraft into a particle moving through a dynamic, many-body system. And many-body systems are notoriously difficult to forecast precisely. This brings us to one of the most beautiful lessons in astronomy. The universe is lawful without always being predictable. Gravity obeys equations with extraordinary precision, yet precise long-term outcomes may remain unknowable because complexity amplifies uncertainty. This is not ignorance. It is the natural consequence of interacting systems. Voyager's future embodies that principle. We can model likely encounters. We can estimate probabilities. We can identify possible stellar flybys. But we cannot map every future interaction over 1 trillion years. Too much changes. Too many influences accumulate. Still, one conclusion grows increasingly clear. Voyager 2 will almost certainly not remain merely a lonely traveller moving away from the Sun forever in perfect isolation. Its path will be shaped, bent, adjusted, quietly rewritten by gravity. And that leads us to the next challenge. If multiple futures are possible, how do scientists compare them? How do we distinguish what is observed from what is inferred and what is truly known from what remains? Hypothesis. To answer that, we must examine the competing models of Voyager's long-term fate. By this point, a pattern has emerged. The farther into the future we look, the less useful certainty becomes. That can feel uncomfortable. Human reasoning often prefers single answers. We want one destination, one map, one definitive future for Voyager 2. Astronomy rarely offers such comfort. Instead, it asks us to separate 4 very different things. Observed fact, measured evidence, scientific hypothesis, unknown. Keeping these categories separate matters because confusion between them often creates false certainty. So before we follow Voyager deeper into time, we need to clarify what scientists genuinely know about its future and what remains model-dependent. Let us begin with fact. Voyager 2 is moving away from the Sun on a hyperbolic escape trajectory. Its present velocity relative to the Sun has been measured with extraordinary precision through decades of tracking. Its current position is also known with remarkable accuracy. These are not guesses. They are measured facts. From these facts, astronomers can calculate near-term motion very reliably. Over decades, centuries, and even many thousands of years, Voyager's trajectory is highly predictable because few strong perturbations are expected. This gives us our first category. Fact Voyager 2 will continue outward from the solar system for a very long time. Now consider evidence. Evidence includes measured properties of the local interstellar medium nearby stellar motions, galactic mass distribution, and the statistical frequency of stellar encounters. This evidence allows scientists to build models. Models are not facts. They are structured interpretation of evidence using physics. A model says if the measured conditions remain within known ranges, then certain outcomes become more probable. This distinction leads us to competing long-term scenarios. Broadly speaking, astronomers can describe Voyager's future using several plausible models. The first is the simplest. Voyager remains an interstellar drifter. In this scenario, no especially close stellar encounter occurs for immense periods of time. Gravity bends the path gradually, but no major event dramatically alters its motion. Voyager simply continues orbiting the galaxy as an inert artifact. This scenario is attractive because it requires no rare events. Given the sparseness of interstellar space, simple drifting may remain the most likely short to medium future. But simple becomes complicated across cosmic time. This leads to the second scenario. Voyager experiences moderate stellar perturbations. In this model, the spacecraft passes near enough to one or more stars for their gravity to noticeably redirect its trajectory. Not capture, not collision, deflection. Think of a river current gently steering floating debris. The object continues moving, but its downstream path changes. This scenario becomes increasingly plausible over millions to billions of years because repeated opportunities accumulate. The third scenario is more dramatic, though far less likely. Temporary gravitational capture. Here, Voyager passes close enough to another star that its motion relative to that star becomes significantly altered, perhaps entering a long orbital trajectory or being temporarily trapped before later escape. This possibility is scientifically interesting because gravitational capture is difficult without energy dissipation. A lone two-body interaction usually cannot produce permanent capture unless additional forces or bodies participate. That means permanent capture by a single star is unlikely. Still, complex multi-body interactions can create unusual outcomes. This places the idea firmly in hypothesis territory. Possible, physically consistent. Not strongly expected. Then comes an even rarer scenario. Collision. Could Voyager strike something substantial? A planet, a moon, a large asteroid, a cometary body? The short answer is yes in principle. The probabilistic answer is almost certainly not for extraordinarily long timescales. Space is simply too empty. Even planetary systems are mostly vacant. Direct impact requires extraordinary alignment. This makes collision the least likely major scenario. Yet it remains non-zero. That phrase appears often in astronomy. Non-zero. Many cosmic possibilities live in that uncomfortable territory between impossible and probable. This brings us to the category people often mishandle. Unknown. Unknown does not mean scientists lack imagination. It means relevant variables cannot be constrained well enough. Voyager's trillion-year future contains enormous unknowns. Consider just a few. Will nearby stars follow expected trajectories without unexpected perturbations? Will the local galactic environment remain broadly similar? Will large-scale gravitational structures evolve in ways current models underestimate? Will interactions involving stellar remnants alter encounter probabilities? Each unknown expands uncertainty, and uncertainty compounds. This compounding produces one of the most important scientific principles in long-range forecasting: error growth. Suppose our measurement of Voyager's current velocity contained a tiny uncertainty so small that it seems irrelevant. Over a day, no meaningful difference. Over a century, still negligible. Over a billion years, tiny errors become vast positional uncertainty. Over 1 trillion years, that uncertainty becomes enormous. This means precise coordinates become physically meaningless. At that scale, we cannot sensibly ask for an exact location. We can only describe regions of probability. This is a difficult shift for the human mind. We prefer deterministic stories. Physics sometimes offers statistical truths instead. A helpful analogy comes from weather. Meteorologists can predict tomorrow's weather fairly well. Next month becomes harder. 10 years becomes nearly impossible in exact detail. Yet climate patterns remain meaningful. Weather is specific. Climate is statistical. Voyager's future works similarly. Near-term trajectory behaves like weather prediction. Far-future fate behaves more like statistical climate. This distinction helps resolve the paradox we introduced earlier. Why can physics be precise yet the future remain uncertain? Because equations can be exact while inputs remain imperfect and systems remain complex. That is not failure of science. It is the honest boundary of prediction. There is another subtle lesson here. Competing models are not enemies. Science does not require a single narrative when evidence supports multiple plausible futures. Instead, competing models sharpen understanding. Each model reveals which assumptions matter most. Each exposes sensitivity. Each highlights unknowns worth studying. In Voyager's case, the models converge on one shared conclusion. Its future is dominated by gravity acting over immense time. where the models diverges in consequence. How much bending? How many encounters? How many meaningful perturbations? And what happens when enough time passes for small differences to become enormous? That final question carries us into the next stage of our journey, because one possible future, though uncertain, deserves special attention. If one particular class of gravitational interaction occurs, Voyager's destiny becomes far stranger than simple drifting. It may cease to behave like a spacecraft escaping the solar system. Instead, it may become something larger, a true galactic wanderer. There is a subtle moment in every long journey when the original point of departure stops defining the traveller. At first, everything is measured relative to home, distance from Earth, distance from the Sun, signal delay, escape velocity. But eventually home becomes less important than the larger environment through which the traveller moves. For Voyager 2, that transition may take tens of thousands to millions of years. And if one particular idea is true, Voyager's identity changes completely. It stops being a spacecraft leaving the solar system. It becomes a galactic object. This possibility emerges from a thought experiment grounded in celestial mechanics. Suppose Voyager experiences repeated gravitational perturbations from passing stars. None is dramatic. None captures it permanently. Each encounter merely alters velocity by a tiny amount and bends direction slightly. A small change. Then another. Then another. Over immense timescales, these changes accumulate. This process resembles diffusion. In physics, diffusion describes how particles gradually spread through repeated small interactions. A drop of ink in water does not teleport across the glass. It disperses through countless microscopic collisions. Voyager may undergo a gravitational analogue, not random motion in the strict sense, but gradual trajectory reshaping through repeated weak encounters. This idea carries profound consequences. If repeated stellar flybys continually alter Voyager's motion, then after enough time its path may no longer preserve meaningful memory of its launch direction. That is a remarkable thought. Right now, Voyager's trajectory still contains a clear historical signature. Its motion reflects a launch from Earth, a gravitational assist from Jupiter, a course shaped by encounters with Saturn, Uranus, and Neptune. Its present path tells a story. In the deep future, that story may blur. Eventually, an outside observer might be unable to infer that Voyager originated from our solar system. Its motion would simply resemble another small inert object orbiting within the Milky Way. At that point, Voyager becomes something conceptually new, not a solar artifact escaping outward, a galactic wanderer embedded in stellar dynamics. This transformation changes how we should visualize its future. Many people picture Voyager traveling in a straight line away from the Sun forever, as though the Sun sits at the center of an expanding map. That mental image quietly assumes the galaxy is fixed. It is not. The Sun itself orbits the galactic center once roughly every 225 to 250 million years. This interval is often called a galactic year. Since dinosaurs disappeared, the solar system has not yet completed a full orbit around the galaxy. That comparison helps reveal scale. Human civilization occupies a tiny fraction of a galactic year. 1 trillion years contains roughly 4,000 galactic orbits. 4,000? During that span, Voyager would experience a galaxy in motion, not a static backdrop. Spiral arms rotate. Stellar associations dissolve. Star formation regions appear and fade. Supernova remnants expand. Clusters disperse. The galaxy continuously rearranges itself. This matters because Voyager's future becomes inseparable from galactic structure. A spacecraft drifting through the sparse stellar suburbs experiences one environment. A trajectory crossing denser regions experiences another. This leads to an important hypothesis. What if Voyager passes through a region of enhanced stellar density? Examples include spiral arms, stellar nurseries, or remnants of dissolving clusters. In such environments, encounter probabilities rise. More nearby stars means more gravitational perturbations. More perturbations means faster diffusion of trajectory. This could accelerate Voyager's transition from solar escapee to galactic wanderer. The evidence for such processes comes from stellar population dynamics. Astronomers studying star clusters observe that gravitational interactions gradually redistribute energy and motion. Objects migrate, scatter, and sometimes escape. Small bodies are particularly sensitive to repeated weak encounters. Voyager, with negligible mass compared to stars, behaves essentially as a test particle. It influences nothing. Everything influences it. That asymmetry matters. Voyager cannot alter stellar motion. Stars can alter Voyagers. This makes its future highly responsive to environment. Now consider a more intriguing possibility. Could repeated interactions eventually place Voyager on an orbit broadly similar to ordinary interstellar debris? The answer appears to be yes. Not quickly, not through a single encounter, but over enough time its motion could become statistically indistinguishable from naturally ejected bodies. This idea becomes even more fascinating when we remember that our solar system has likely ejected countless natural objects. Comets, asteroids, fragments from ancient collisions, planetary debris. Many such bodies now drift through interstellar space. In fact, the discovery of Oumuamua and 2I/Borisov confirm that interstellar objects pass through planetary systems. This tells us something profound. The galaxy is already populated with wandering material. Voyager may eventually join that population in a dynamical sense. That creates a striking reversal. We launched Voyager as something extraordinary, a singular artifact of intelligence. Over cosmic time, gravity may erase that dynamical uniqueness. Its trajectory may become ordinary. Its physical nature remains extraordinary. Its motion may not. There is quiet beauty in that. Human intention launched the spacecraft. Cosmic mechanics may eventually absorb it into the statistical background of galactic wandering. Not destroyed, not forgotten physically, but dynamically blended into the larger population of drifting objects. And yet one question remains unresolved. Even if Voyager becomes a galactic wanderer, what kind of galaxy will it inhabit? We often speak of the Milky Way as though it were timeless. But galaxies evolve. Stars die. New stars form. Mass redistributes. Entire galactic neighborhoods transform. So perhaps the deeper mystery is no longer Voyager's motion alone. Perhaps the greater mystery is the changing galaxy through which it moves. Because if Voyager survives long enough, the Milky Way it travels through may become almost unrecognizable compared with the galaxy we know today. By now, Voyager 2 has changed in our imagination. It began as a spacecraft leaving Earth. Then it became a machine crossing the edge of the solar system. Now it has become something larger, a small artifact moving within the gravitational architecture of the Milky Way. To understand its trillion-year future, we must widen our scale once again. We must stop thinking like planetary observers. We must think like galactic observers. From Earth, the Milky Way appears serene, a luminous band stretching across dark skies, soft and almost motionless to human perception. For ancient civilizations, it seemed permanent, a celestial river fixed across generations. But permanence is another human illusion. Galaxies are not still. They are vast dynamic systems composed of stars, gas dust, dark matter, magnetic fields and gravitational flows operating across immense timescales. The Milky Way contains hundreds of billions of stars and spans roughly 100,000 light-years across its visible disk. Our solar system resides far from the centre in a relatively quiet outer region known as the Orion Arm between larger spiral arms. This location has likely mattered for life. Too close to the galactic centre and radiation stellar density and gravitational disturbances increase dramatically. Too far into the sparse outskirts and heavy elements become less abundant, limiting planet formation. We live in a comparatively stable neighbourhood. Voyager 2 begins its galactic life from this suburb. That detail matters because the local galactic environment strongly influences long-term encounters. Dense regions produce more interactions. Sparse regions produce fewer. Right now, the Sun moves through a relatively calm stellar neighbourhood. The average distance between nearby stars remains several light-years. Catastrophically close encounters are rare, but rare is not permanent. Over millions of years, orbital motion carries the solar system through changing galactic environments. The Sun orbits the galactic centre at roughly 220 kilometers per second, completing one orbit approximately every 230 million years. This journey is not a perfect circle. The solar system oscillates vertically above and below the galactic plane while orbiting inward and outward slightly over time. This produces a complex path. Voyager 2 inherits that motion. Even after escaping the Sun's immediate gravitational dominance, it remains embedded in this broader galactic orbit. This leads to a crucial realization. Voyager is not travelling through the galaxy the way a ship crosses an ocean. It is already part of the galaxy's motion. The galaxy carries Voyager with it. That changes how we think about distance. When people ask where Voyager will be in 1 trillion years, they often picture linear travel outward. But outward from what? From the Sun, yes. From the galaxy, not necessarily. Unless some future interaction radically changes its velocity, Voyager remains gravitationally bound to the Milky Way. That means its future resembles orbital wandering rather than escape into intergalactic void. This distinction is profound. Escaping the solar system sounds dramatic. Escaping a galaxy is vastly harder. Galactic escape velocity in our neighbourhood is hundreds of kilometres per second, far beyond Voyager's speed. Voyager is fast enough to leave the Sun. It is nowhere near fast enough to leave the Milky Way. So in the absence of extraordinary gravitational assistance, Voyager's trillion-year future remains a galactic story. That raises the next question. What happens to an object orbiting a galaxy for thousands of galactic years? The answer begins with differential motion. Not all parts of a galaxy rotate at the same angular rate. Inner regions orbit faster than outer ones. Stars move on slightly different paths depending on mass distribution and local perturbations. This gradual shearing changes stellar neighbourhoods continuously. Constellations dissolve because stars move independently. Clusters disperse. Associations break apart. The sky changes. Over a few million years, the changes become noticeable. For hundreds of millions dramatic, over billions complete, Voyager experiences all of this. The familiar stars surrounding the solar system today will not remain familiar. Nearby stellar neighbours will change repeatedly. Some stars move away, others move closer. Entire regions of the sky become unrecognisable. This dynamic rearrangement has an important consequence. The probability landscape surrounding Voyager changes constantly. A quiet region today may become denser later. A denser region may disperse. Future encounters cannot be understood using today's sky alone. We must think statistically. This statistical approach reveals something elegant. Over sufficiently long timescales, trajectories through the galaxy become influenced by repeated weak perturbations that slowly redistribute orbital properties. Astronomers call related processes dynamical heating. Over time, gravitational interactions can increase the random component of stellar motion. Objects gradually acquire more vertical oscillation, more eccentricity, more deviation from initially smooth orbits. In simple terms, orbits become messier. Voyager as a tiny, low-mass object is especially susceptible to cumulative perturbations. This means its galactic path may slowly randomize. Not completely, not instantly, but enough that after immense time reconstructing its original trajectory becomes nearly impossible. And yet gravity is not the only large-scale factor. The galaxy contains invisible mass. Most of the Milky Way's mass is not in stars or gas, but in something far more mysterious. Dark matter. Astronomers infer dark matter through gravitational effects on galactic rotation and structure formation. Without it observed, orbital velocities make little sense. We cannot see dark matter directly. We observe its influence. This matters because Voyager moves within a gravitational potential dominated partly by something invisible. Even at galactic scale, unseen structure shapes motion. This introduces a philosophical echo from earlier chapters. Again and again, Voyager's journey reveals hidden architecture, solar magnetic boundaries, interstellar structure, stellar encounters, galactic mass. Invisible forces shape visible outcomes. The deeper we look, the less empty space appears. And there is one more reason to widen our perspective. The Milky Way itself is not isolated. It belongs to a larger gravitational environment filled with satellite galaxies, dark matter halos, tidal interactions, and one especially significant neighbour, a massive spiral galaxy moving steadily toward us. Its future collision will transform the Milky Way itself, which means that Voyager's future is not only shaped by the galaxy we know now, It may be shaped by the galaxy our Milky Way eventually becomes. So far, Voyager 2's journey has seemed to unfold across nested scales. First the solar system, then interstellar space, then the Milky Way. Each time we widened our perspective, the same lesson returned. What looks simple at one scale became more complex at the next. Now those scales begin to connect, because the forces shaping Voyager's future are not independent layers stacked neatly apart from one another. They overlap, they interact, they influence one another in ways that are easy to miss when studied separately. This is where astronomy becomes especially rewarding. Patterns that once felt unrelated suddenly reveal hidden connections. One such connection begins with stars. At first glance, stars seem like local actors. They illuminate planetary systems, host worlds, and shape nearby gravitational environments. But stars also influence the galaxy at large. Massive stars live short lives and die violently as supernovae, ejecting heavy elements and energy into interstellar space. These explosions compress gas clouds, trigger new star formation, and carve cavities into the galactic medium. In other words, stars continuously reshape the environment through which Voyager travels. The space between stars is partly a memory of stars that died long ago. That idea alone is beautiful. Voyager is moving not through generic emptiness, but through a landscape sculpted by ancient stellar history. Gas clouds, magnetic structures, shock fronts, ionized bubbles, all of them carry traces of stars that once burned. This creates our first unexpected connection. The local interstellar medium discussed earlier is linked directly to stellar evolution. The environment around Voyager exists because stars lived and died. Now consider a second connection. Stellar motion shapes encounter probability. As stars orbit the galactic center, they change local density, neighborhood structure, and gravitational interaction rates. But those stellar orbits are themselves shaped by galactic mass distribution, spiral arm dynamics, and dark matter. This means a close stellar encounter affecting Voyager is not merely a star-level event. It is partly a galactic event. The galaxy influences the stars. The stars influence Voyager. Small-scale outcomes inherit large-scale structure. That hierarchy matters because it reveals why long-term prediction becomes so difficult. Each level introduces uncertainty, planetary history, stellar dynamics, galactic evolution. Each uncertainty feeds the next. This cascading complexity creates a striking parallel with another field of science, climate systems. Weather at a local point depends on planetary scale circulation, ocean dynamics, solar heating, and atmospheric chemistry. Small-scale events reflect large-scale processes. Voyager's future behaves similarly. A tiny change in galactic environment may alter stellar encounter statistics, which alters gravitational perturbations, which changes trajectory. Large structures quietly influence small artifacts. There is another connection even more surprising. The same gravity that perturbs Voyager also organizes the long-term fate of planetary systems. Over millions to billions of years, stellar flybys can disturb outer comet reservoirs such as the Oort cloud. This can send comets inward towards stars. Our own solar system has likely experienced such disturbances many times. That means the forces gradually bending Voyager's path are similar to the forces that occasionally reshape comet populations. A spacecraft and a comet may experience related gravitational histories. That comparison changes how Voyager appears. It begins to look less like a machine and more like a small celestial body. Not because its origin changes, because the laws governing its motion increasingly resemble those governing natural objects. This is one of the quiet paradoxes of deep time. Human-made artifacts eventually become subject to cosmic processes indistinguishable from those affecting natural debris. Technology does not escape physics. It joins it. Voyager embodies that transition. There is still another hidden connection. Time. Not human time. Cosmic time. Earlier we treated millions, billions, and trillions of years mainly as large intervals. But time does more than accumulate motion. Time transforms environments. This matters because Voyager's trajectory alone tells only half the story. Even if Voyager moved predictably, the galaxy around it would not remain fixed. And the most dramatic galactic transformation already has a name. Andromeda Galaxy. Located about 2.5 million light-years away, Andromeda is moving toward the Milky Way. Measurements of relative motion indicate that the two galaxies are gravitationally bound and on a collision course. The word collision can sound violent, but galaxies are mostly empty space. Individual stars rarely strike one another directly. Instead, the merger reshapes gravitational structure. Spiral disks distort. Tidal streams form. Stellar orbits redistribute. Gas clouds compress. Star formation may surge. Over billions of years, the Milky Way and Andromeda will merge into a larger galaxy, sometimes informally called Milkomeda. This future merger creates a profound connection to Voyager. If Voyager survives long enough, it may witness not consciously but physically endure one of the largest transformations in our galactic history. That possibility reframes everything. Voyager's future is not merely about moving through a galaxy. It is about surviving the evolution of a galaxy. And that evolution affects gravitational structure. New orbital paths emerge. Encounter rates change. Mass distribution shifts. The probability landscape itself transforms. This makes one truth unavoidable. Voyager's trillion-year future cannot be understood by projecting today's Milky Way unchanged into the future. That would be like predicting Earth's weather for 1 billion years while assuming continents never move. The framework itself changes. This is the deeper connection between all our previous chapters. Boundaries blur because systems evolve. Solar boundaries shift. Interstellar environments shift. Stellar neighborhoods shift. Galaxies shift. Nothing remains frozen. Not even structures that feel eternal. That realization carries philosophical weight. Humans often seek permanence. Astronomy repeatedly reveals process instead. Not fixed states. Flows. Transformations. Evolution across scales. Voyager 2, though silent and mechanical, becomes an extraordinary witness to this truth. Its path records the universe not as a static stage but as an unfolding process. And that leads naturally to the next question. If galaxies themselves evolve so dramatically, what does modern astronomy actually tell us about the cosmic future that Voyager may inhabit? Because the farther ahead we look, the stranger and quieter the universe becomes. Modern astronomy has given humanity something extraordinary. For most of history, people studied the cosmos by looking upward and waiting for light to arrive. The universe revealed itself slowly through naked eye observation, then through telescopes that gathered more photons, and later through instruments capable of detecting radio waves, X-rays, infrared radiation, and gravitational waves. Today we do something even more remarkable. We simulate the universe. Supercomputers now model the growth of cosmic structure across billions of years, tracing how matter collapses into galaxies, how stars form, and how gravitational interactions reshape systems over time. Combined with observations from space telescopes and deep surveys, these simulations allow astronomers to peer not only into cosmic history, but also into plausible futures. That matters enormously for understanding the long-term environment of Voyager 2, because Voyager's future depends not just on its motion, but on the future evolution of the cosmos around it. Let us begin with what modern observations tell us about galaxies. Recent observations from James Webb Space Telescope Hubble, Space Telescope, and large sky surveys reveal that galaxies are more dynamic than earlier generations suspected. They accrete gas merge with companions, exchange tidal material, and continuously recycle matter through stellar birth and death. Even quiet spiral galaxies are not static disks. They are living gravitational systems. The Milky Way itself is currently absorbing smaller satellite galaxies. Astronomers have identified stellar streams, vast elongated trails of stars that serve as fossils of past mergers. These streams reveal that galactic growth often occurs through gradual accretion. In other words, our galaxy is still assembling itself. Voyager exists within a structure that remains under construction. This matters because every merger alters the galactic gravitational potential. Even modest mergers redistribute mass. Mass redistribution changes orbits. Changing orbits changes encounter probabilities. A spacecraft that seems dynamically isolated today may inhabit a very different gravitational environment after enough galactic evolution. Simulations help quantify these changes. Large cosmological simulations such as Illustris, Eagle, and Millennium have shown that galaxies evolve through long sequences of mergers interactions, feedback processes, and structural transformations. Spiral arms appear, fade, and reform. Stellar disks thicken. Halo structure changes. No single galactic configuration lasts forever. That conclusion reinforces something we've seen repeatedly. Voyager's future cannot be separated from cosmic evolution. There is another modern discovery, even more relevant. The universe is expanding. This idea is familiar to many people, but its implications remain deeply counterintuitive. Space itself expands on large scales. Galaxies sufficiently far apart recede from one another as cosmic expansion stretches the metric of space. Yet this expansion behaves differently depending on scale. Inside galaxies, gravity dominates. Inside galaxy groups, gravitational binding often resists expansion. At larger cosmic scales, expansion wins. This distinction matters for Voyager. Voyager is far too deeply embedded within gravitationally bound structures for cosmic expansion to pull it away from the Milky Way directly. This is an important clarification. People sometimes assume expansion means everything drifts apart uniformly. That is not how cosmic expansion works. Atoms do not expand. Solar systems do not expand. Galaxies generally do not expand internally. Bound systems resist expansion. So Voyager will not gradually drift away because the universe expands. Gravity within the local galactic environment remains far stronger. Still, expansion matters indirectly, because it shapes the long-term fate of large-scale cosmic structure. Modern observations suggest the expansion of the universe is accelerating, driven by something we call dark energy. Dark energy remains one of the deepest mysteries in physics. We do not fully understand its nature. We observe its effect, acceleration. As cosmic expansion accelerates, distant galaxies gradually recede faster. Over immense timescales, galaxies beyond the local gravitational group may disappear beyond observable reach. This leads to a haunting future. In trillions of years, if dark energy behaves as current models suggest, the descendants of the Milky Way may become increasingly isolated. Most distant galaxies may vanish beyond observable horizons. The night sky would look profoundly different. This matters for Voyager because it tells us something about the large-scale universe it may inhabit. The cosmic backdrop itself becomes quieter, less populated visually, less connected observationally, a lonelier cosmos. Modern simulations also reveal another long-term trend. Star formation is slowing. The universe still forms stars, but not at the rate seen billions of years ago. The peak era of star formation occurred long ago. Since then, gas reservoirs have gradually depleted or become harder to cool into new stellar nurseries. This means the stellar future of the cosmos is calmer than its past. Fewer new stars, more aging populations, more stellar remnants, white dwarfs, neutron stars, black holes. These remnants matter for Voyager because they alter encounter possibilities. Future stellar neighborhoods may contain fewer luminous stars and more compact remnants. That changes the nature of gravitational encounters. A white dwarf exerts gravity no less effectively than the star that preceded it, provided mass remains comparable. Light fades, gravity persists. This is another recurring theme. Visible change and gravitational influence are not the same thing. The cosmos may become darker while remaining dynamically active. Modern astronomy also provides insight into the survival of small objects. Simulations of long-lived planetary debris suggest that minor bodies can persist for immense periods unless disrupted by collisions, tidal encounters, or engulfment during stellar evolution. This supports an important inference. Voyager as a small inert object could survive far longer than its operational lifetime by many orders of magnitude. Its electronics may die in decades. Its structure may persist for billions or more. That gap between functional death and physical survival is central to our documentary. Modern astronomy gives us confidence in broad environmental trends: galactic evolution, accelerating expansion, declining star formation, long-lived gravitational structure. But confidence in trends is not certainty in details. And that brings us to the frontier of honest science. For all that modern astronomy has revealed, there remain profound things we still do not know, especially when our timeline stretches from billions to trillions of years. The deeper astronomy looks into the cosmos, the more precise its measurements become, and yet precision has produced an unexpected kind of humility. We know more than any civilization before us. We can measure stellar motion to extraordinary accuracy. We can track spacecraft across billions of kilometers. We can reconstruct galactic histories and model cosmic evolution with remarkable sophistication. Still, some of the most important questions remain unanswered. This is not a contradiction. Knowledge often reveals the scale of what remains unknown. That is especially true when asking where Voyager 2 will be in 1 trillion years. By now we understand something essential. The problem is not lack of physics. It is compounded uncertainty. Each chapter has introduced variables: local stellar encounters, galactic evolution, dark matter distribution, cosmic expansion, material survival. Each variable carries uncertainty. When combined across trillions of years, uncertainty becomes the central story. Let us examine what scientists still do not know. The first major unknown is the detailed future of nearby stars. This may sound surprising because stellar motion is measurable with extraordinary precision. Missions such as Gaia have mapped the positions and velocities of more than 1 billion stars, transforming our understanding of the Milky Way. Yet precision today does not guarantee precision forever. A star's future path depends not only on its current motion, but also on countless future perturbations. Passing stars alter trajectories. Galactic tides matter. Mass redistribution matters. Over long enough timescales, tiny uncertainties grow. This means we cannot know every future stellar flyby affecting Voyager. We can estimate encounter rates. We cannot map exact histories. The second unknown involves dark matter. Dark matter dominates much of galactic mass, yet its true nature remains unresolved. Is it composed of undiscovered particles? Does it cluster at small scales more strongly than current models suggest? Could subtle substructures alter long-term trajectories in ways not fully captured by present simulations? These are open questions. Even if dark matter influences Voyager only weakly at small scales, weak effects integrated across immense time deserve respect. The third unknown concerns galactic transformation. We know the Milky Way and Andromeda Galaxy will likely merge, but the detailed outcome remains model-dependent. Orbital parameters, mass loss, satellite interactions, gas dynamics, all affect the merger's final structure. Will the remnant galaxy be more spheroidal? How chaotic will orbital redistribution become? What new stellar encounter probabilities merge afterward? We know the broad story, not every detail. The fourth unknown is even deeper: dark energy. Modern cosmology strongly supports accelerated expansion, but the underlying physics remains mysterious. Current models often treat dark energy as a cosmological constant, a stable energy density inherent to space-time itself. But what if that assumption is incomplete? Some alternative models propose evolving dark energy. Others suggest new gravitational physics. Most current evidence supports standard cosmology, but trillion-year forecasts inevitably inherit uncertainty from foundational cosmological questions. This matters because cosmic expansion shapes the far future environment surrounding all galaxies. Then there is material uncertainty. We have discussed Voyager as though it remains structurally intact for immense timescales. That assumption is reasonable. It is not guaranteed. Materials age, radiation damages atomic lattices, micrometeoroid impacts accumulate, thermal cycling alters stresses, even tiny degradation becomes meaningful over extreme durations. There is no laboratory capable of directly testing trillion-year survival. Instead, we extrapolate from physics and observed material behavior. Extrapolation is powerful. It is not certainty. The Golden Record provides a particularly interesting case. The Voyager Golden Record is plated in gold partly because gold resists corrosion. In deep space that offers extraordinary longevity, but perfect preservation is unlikely forever. Surface erosion radiation effects and particle impacts slowly alter material. How much detail remains readable after vast timescales? That is not fully known. There is also a subtle unknown most people overlook. Unknown unknowns. Science usually focuses on identified uncertainties, but the universe sometimes surprises us with phenomena we had not anticipated at all. History repeatedly teaches this lesson. Before the 20th century, no one knew about neutron stars. Before radio astronomy, pulsars were unimaginable. Before modern cosmology, dark energy was unknown. This pattern encourages scientific humility. The future may include relevant phenomena we do not currently recognize. That humility is not pessimism. It is discipline. Science grows strongest when it distinguishes confidence from certainty. There is another profound unknown, chaos itself. Earlier we described chaotic systems as highly sensitive to initial conditions. This creates a practical boundary to prediction. Even if every law remains known, perfect long-range forecasting may remain impossible because finite precision inevitably grows insufficient. This introduces a philosophical boundary. There may be futures that are physically determined yet epistemically inaccessible. In simpler terms, reality may evolve according to exact laws while remaining fundamentally unpredictable to observers with finite knowledge. Voyager's trillion-year future may live inside that boundary. Not unknowable because physics fails. Unknowable because information limits prediction. That distinction matters deeply. It changes how we interpret unanswered questions. Uncertainty does not always mean missing theory. Sometimes it means irreducible complexity. This is one of the most mature insights in modern science. Not every question yields exact coordinates. Some yield probability distributions. Some yield constraints. Some yield only ranges of possibility. And yet uncertainty should not diminish wonder. If anything, it enlarges it. Because uncertainty reminds us that the universe is not merely a solved puzzle awaiting lookup. It remains an active frontier. Even for something as simple seeming as a silent spacecraft drifting through space. This brings us to the edge of current knowledge. We have identified what we know. We have identified what we can model. We have identified what remains uncertain. Now we must confront the harder question. Where exactly does scientific prediction begin to fail? At what point does the future stop being something we can calculate and become something we can only contemplate? That boundary, the edge of knowledge, is the next frontier in our journey. There is a difference between not knowing an answer and reaching the limit of what can meaningfully be known. That distinction defines the frontier of science. Throughout this journey, we have repeatedly extended our view outward. We began with a spacecraft, then the solar system, then interstellar space, then the Milky Way, and finally the broader cosmic environment. At every scale, physics gave us powerful tools. But powerful is not infinite. Eventually, prediction itself encounters a boundary. This boundary is not a physical wall in space. It is a boundary in knowledge, a limit imposed by measurement precision, computational complexity, chaotic dynamics, and perhaps by nature itself. To understand this limit, consider what prediction requires. At minimum, we need three things: accurate laws, accurate measurements, sufficient computation. Modern physics gives us remarkably accurate laws for celestial motion. The equations governing gravity are among the most successful descriptions ever developed in science. For most astronomical purposes, they work extraordinarily well. So the first requirement is largely satisfied. The second requirement is harder. Measurements never perfect. No instrument produces infinite precision. Every observation contains uncertainty. Usually that uncertainty is tiny. For near-term forecasting, tiny uncertainty barely matters. For trillion-year forecasting, tiny uncertainty becomes decisive. A helpful analogy comes from navigation at sea. Suppose a ship begins a journey with a directional error so small that no human could notice it, perhaps a fraction of a degree. After 1 kilometre, the deviation is negligible. After 1,000 kilometres, the ship may miss its destination by a vast margin. Tiny angular differences grow into enormous spatial differences. Voyager 2 faces the same principle. Its current position and velocity are measured with extraordinary precision, but not infinite precision. Those tiny uncertainties propagate forward. Now add gravitational perturbations. Each future stellar encounter introduces further uncertainty. Each encounter changes sensitivity to later encounters. Error compounds. Prediction weakens. The third requirement, computation, introduces another limit. Even if measurements were perfect, calculating the exact long-term behavior of many interacting bodies can become computationally intractable. This is the famous many-body problem. Two-body gravitational systems are elegantly solvable. Three-body systems become dramatically harder. Large interacting systems quickly exceed analytical simplicity. The galaxy contains hundreds of billions of stars. Add gas clouds, stellar remnants, dark matter substructure, and evolving mass distributions, and the computational challenge becomes immense. Simulation helps. Approximation helps. But exact long-range prediction becomes increasingly unrealistic. This leads us to the edge of knowledge. Not ignorance. Not failure. A natural horizon beyond which precision loses meaning. Astronomers encounter such horizons often. Planetary systems can be stable for billions of years while still exhibiting chaotic behavior in fine detail. Climate systems obey physical law while remaining impossible to predict exactly far into the future. Quantum mechanics adds another layer, reminding us that uncertainty is woven into measurement itself. Voyager's future lies at the intersection of these limits. Classical gravity governs most of its motion. Chaotic sensitivity amplifies uncertainty. Finite measurement constrains prediction. This combination creates what might be called practical unpredictability. The distinction matters. Practical unpredictability does not mean anything can happen. Physics still constrains possibilities. Voyager will not spontaneously accelerate to light speed. It will not violate conservation laws. It will remain subject to gravity momentum and material limits. Possible futures remain bounded. Exact futures do not. That realization changes the nature of our question. Early in this documentary, where will Voyager 2 be in 1 trillion years sounded like a coordinate problem. Now it sounds different. It sounds like a probability question constrained by physical law. This transformation mirrors a deeper scientific pattern. As systems grow more complex, science often shifts from deterministic description to probabilistic understanding. That shift can feel less satisfying emotionally. It is often more honest intellectually. There is another frontier we must acknowledge. The frontier of theory itself. We often assume today's physics will remain complete. History advises caution. Isaac Newton described gravity with extraordinary success. Centuries later, Albert Einstein revealed a deeper description through general relativity. Newton was not discarded. He was contextualized. Likewise, modern physics may someday be expanded by deeper theories. Quantum gravity, dark matter, dark energy, space-time structure, these remain incomplete frontiers. This matters because trillion-year extrapolation quietly assumes no radically relevant new physics emerges. That assumption is reasonable. It is still an assumption. Science must remain open to revision. This introduces a fascinating philosophical point. The farther we project into the future, the more our predictions depend not only on current measurements, but on confidence in current theory. That confidence is high. It is not absolute. So where exactly is the edge of knowledge? There is no single date, no exact threshold. Instead, the edge appears gradually. For decades ahead, Voyager's motion is highly predictable. For thousands of years, still meaningful. For millions, increasingly statistical. For billions, highly uncertain in detail. For trillions, exact prediction dissolves almost completely, and yet broad truths survive. This is important. Even beyond the predictive horizon, certain large-scale conclusions remain robust. Voyager will likely remain gravitationally bound to galactic structure unless extraordinarily perturbed. It will almost certainly outlive its electronics. It may survive longer than civilizations. It will inhabit a cosmos that changes profoundly around it. These truths endure even when coordinates vanish. That is the paradox of knowledge. The closer we approach ultimate detail, the more certainty fades. The broader the scale, the more stable certain patterns become. Exact position becomes unknowable. Cosmic trends remain meaningful. This boundary is not frustrating. It is beautiful, because it reminds us that science is not the elimination of mystery. It is the refinement of mystery. The unknown becomes sharper, more precise, more meaningful. And now, standing at that frontier, another question emerges. If we cannot know Voyager's exact location in the deep future, what can we still know with confidence about the universe it will inhabit? The answer leads to the largest implications of all. Not about trajectory, about reality itself. There is a quiet shift that happens when questions about motion become questions about reality. At first, this documentary asks something seemingly narrow. Where will Voyager 2 be in 1 trillion years? By now, that question has expanded far beyond spacecraft navigation. It has become a question about what kinds of structures endure, what survives, what changes, what remains meaningful when time stretches beyond civilization, beyond planets, and even beyond stars. In that sense, Voyager has become a lens, not because the spacecraft is physically important to the cosmos. Compared with stars, galaxies, or even asteroids, it is insignificant. Its importance comes from contrast. Voyager is tiny. Time is vast. And that contrast reveals deep truths about reality. One of those truths concerns permanence. Human perception evolved around short-lived structures. Mountains feel permanent. Oceans feel permanent. Continents feel permanent. Civilizations often imagine themselves as enduring. Astronomy gently dismantles that intuition. Mountains erode. Oceans vanish. Continents drift. Stars die. Galaxies merge. Even structures that appear eternal are usually temporary processes unfolding slowly enough to feel static. Voyager exposes this beautifully. From a human perspective, the spacecraft appears durable beyond comprehension. It may survive far longer than monuments, archives, and cities on Earth. That makes it feel permanent. From a cosmic perspective, even Voyager is temporary. Materials degrade. Collisions remain possible. Entropy advances. Nothing material remains untouched forever. This brings us to one of physics' deepest ideas. Entropy. Entropy is often described as disorder, but a more useful intuition is dispersal. Energy spreads. Useful gradients fade. Differences smooth out. Hot becomes cold. Structured becomes diffuse. Ordered systems require energy flows to maintain complexity. Civilizations require energy. Biology requires energy. Stars shine because energy gradients remain available. When gradients disappear, complexity becomes harder to sustain. Voyager's future sits inside this universal tendency. Today, the spacecraft is highly ordered. Circuits arranged deliberately. Components placed with purpose. Information encoded in structure. That order exists because intelligence imposed low entropy locally. But over immense time, order erodes. Not instantly. Not dramatically. Gradually. The Golden Record remains readable only while structure survives. The antenna remains recognizable only while geometry persists. Entropy does not destroy meaning in one moment. It slowly dissolves distinctions. This idea scales upward. The same thermodynamic logic shaping Voyager also shapes stars and galaxies. Stars shine because gravitational collapse creates hot, dense cores capable of nuclear fusion. Fusion releases usable energy. Eventually fuel runs low. Stellar structure changes. Stars age. Entropy advances. Galaxies themselves are not exempt. Galactic structure persists while energy flows and gravitational interactions sustain complexity. Over immense timescales, systems relax. Energy redistributes. Order changes form. This leads to a larger implication. Voyager's future is not only about motion through space. It is about motion through thermodynamic history. That phrase deserves attention. Thermodynamic history. The universe has an energetic age. The early cosmos was hot, dense, and dynamic. Stars formed rapidly. Galaxies assembled vigorously. Collisions were common. The modern cosmos is calmer. In the far future, calm deepens further. This progression tells us something profound. Time changes, not just positions. It changes possibility. Certain kinds of structures become easier in some cosmic eras and harder in others. Life, as far as we know, depends on energy gradients. Civilization depends on stable environments and accessible energy. Technology depends on matter remaining structured. Voyager exists because the universe currently supports such complexity. That support is not guaranteed forever. This raises an extraordinary philosophical implication. Voyager may outlive humanity. It may outlive Earth. It may outlive the Sun. In doing so, it becomes a physical bridge between cosmic eras. An artifact born in a biologically rich universe that may persist into a far quieter one. Few human-made objects can even be discussed on such timescales. Voyager can. There is another implication even deeper. Information. Physics increasingly treats information as fundamental. The arrangement of matter carries information. DNA carries information. Computer memory carries information. The Golden Record carries information. As Voyager ages, its physical structure preserves information about human civilization. Not complete information, not enough to reconstruct humanity perfectly, but enough to encode evidence of intelligence. This makes Voyager more than material. It becomes stored information moving through space-time. That framing changes the emotional meaning of its journey. We often think of exploration as discovery. Voyager also represents preservation, a fragment of Earth exported beyond Earth, a durable physical memory. This raises a haunting question. If all observers disappear, what remains of meaning? The Golden Record contains music greetings, images, and intention, but meaning requires interpretation. Without minds, information persists physically but not semantically. The grooves remain. Meaning sleeps. This distinction reveals something profound about reality. Matter can preserve patterns. Consciousness interprets them. Voyager may survive physically while the civilization that gave it meaning vanishes. In that case, what remains? Pattern without observer. Structure without memory. This is not merely philosophical. It touches a deep question in cosmology. How much of reality is structure and how much is interpretation? Voyager cannot answer that, but it embodies the question. And that question becomes even more powerful when we look farther ahead. Because we've discussed stars evolving, galaxies merging, and entropy increasing. But one transformation remains larger than all others, the eventual death of the Sun. When that happens, the birthplace of Voyager changes forever. And if Voyager survives beyond that moment, it will become something almost impossible to emotionally comprehend. A messenger still travelling long after the world that sent it is gone. There's a profound difference between deep time and far future. Deep time allows us to think about durations beyond ordinary experience. The far future asks something harder. What will reality itself become? By now we understand that exact prediction of Voyager 2 becomes impossible across 1 trillion years. But while precise coordinates fade into uncertainty, large-scale cosmic evolution remains easier to describe. And that evolution is quieter than many expect. Not catastrophic, not explosive. Quiet, slow, cooling, dimming, a gradual reduction of activity. To understand Voyager's far future, we begin with the most immediate large transformation relevant to its origin. The death of the Sun. The Sun is currently about 4.6 billion years old, roughly halfway through its main sequence lifetime. For now, hydrogen fusion in its core provides stability. Gravity pulls inward. Thermal pressure pushes outward. The balance holds. It will not hold forever. In roughly 5 billion years, the Sun's hydrogen fuel in the core will become depleted. Fusion dynamics will change. The core will contract. Outer layers will expand. The Sun will become a red giant. Its radius will grow enormously. Inner planets face profound consequences. Mercury will almost certainly be consumed. Venus almost certainly as well. The fate of Earth is more complex, but the outlook is grim even under optimistic models. Long before engulfment becomes relevant, Earth's surface will become uninhabitable. Oceans evaporate. Climate destabilizes. Complex surface life becomes impossible. This transformation matters for Voyager not because the spacecraft is threatened directly. Voyager will already be far beyond danger. It matters symbolically. The birthplace of Voyager will be gone. Not merely transformed politically or biologically, physically altered beyond recognition. The planet that launched the spacecraft may no longer exist as a habitable world. That alone reshapes our emotional understanding of the mission. Voyager was launched by a civilization under blue skies, liquid oceans, and living biospheres. Its journey may continue long after those conditions disappear forever. After the red giant phase, the Sun will shed outer layers and form a planetary nebula. Its remaining core becomes a white dwarf. A white dwarf is not a star in the active fusion sense. It no longer generates energy through nuclear burning. Instead, it shines from residual heat, slowly cooling, slowly fading. The future solar system becomes much darker. Yet gravity remains. The white dwarf retains much of the Sun's mass. Its gravitational influence continues. Light changes. Gravity persists. This phrase has returned repeatedly throughout our journey because it captures one of cosmic evolution's deepest truths. Visible transformation often exceeds gravitational transformation. The universe can become darker while remaining dynamically alive. Now extend our view beyond the solar system. The next major transition concerns stars across the galaxy. Star formation continues declining. Gas reservoirs shrink. Eventually, the era of active star birth slows dramatically. Bright young stars become rarer. The cosmos gradually fills with older stellar populations and stellar remnants. White dwarfs become common. Neutron stars remain. Black holes persist. In 1 trillion years, the universe will still contain stars. Many long-lived red dwarfs can burn for trillions of years because they consume fuel extremely slowly. This detail matters. 1 trillion years sounds impossibly distant, yet it does not represent the absolute end of stellar light. Some stars endure, especially low-mass red dwarfs. This is important because it grounds our discussion scientifically. When we speak of a darker future, we must avoid exaggeration. 1 trillion years lies deep in the far future, but not at the final thermal death of the universe. There may still be luminous stars. Still, the cosmic environment will differ profoundly from today. Massive stars will be gone. Many sun-like stars will be dead. Bright stellar nurseries will be far rarer. The galaxy becomes older, redder, quieter. Voyager, if still intact, drifts through this aging cosmos. And the galaxy itself may no longer resemble today's Milky Way. By then, the merger with Andromeda Galaxy will be ancient history. The resulting merged galaxy may resemble a giant elliptical system with less pronounced spiral structure and reduced star formation. Stellar orbits become more randomized. The graceful spiral architecture familiar to us may be gone. This means Voyager's trillion-year environment may differ in every intuitive way from its birthplace. Different stellar population, different galactic structure, different sky, different radiation environment, and perhaps different neighbouring objects. There is another subtle possibility. Over such vast timescales, gravitational interactions can eject stars and smaller bodies from galaxies. Some objects gain sufficient energy through repeated encounters to escape into intergalactic space. Could Voyager eventually do this? In principle, yes. But this would likely require extraordinarily favourable gravitational interactions. Without such rare events, Voyager probably remains bound to galactic structure. Still, the possibility matters because it illustrates how strange deep time becomes. Even seemingly impossible trajectories become non-zero possibilities. This brings us to the largest long-term trend of all, cosmic isolation. Because of dark energy and accelerating expansion structures beyond our local gravitational group become increasingly unreachable, distant galaxies fade beyond cosmic horizons. The observable universe shrinks in practical terms, not because space contracts, because accessible information disappears. Observers in the far future may see far less evidence of the broader cosmos than we do today. That idea carries profound irony. We may live in one of the best eras for cosmology. The universe currently reveals its large-scale history to observers. Far future civilizations may not have that luxury. Voyager born during this privileged era may carry physical evidence from a time when cosmic structure was more visible. And that brings us to the final approach toward our original question. We have explored stars, galaxies, entropy, uncertainty, and cosmic aging. Now only one step remains. We must return to the question that began everything. Not with exact coordinates. With perspective. After 1 trillion years, what does it truly mean to ask where Voyager 2 will be? We began with a simple belief. Every journey ends somewhere. That belief felt natural because human experience trains us to think in destinations. A road leads to a city. A ship reaches a harbour. A spacecraft reaches a planet, lands, or falls silent. But after travelling with Voyager 2 through scales of space and time far beyond ordinary intuition, that belief no longer feels adequate. The question has changed. Not because the original question was wrong, because we now understand how much it contained. Where will Voyager 2 be in 1 trillion years? At the beginning this sounded like a coordinate problem, a location, a point in space. perhaps a nearby star, perhaps the outer galaxy, perhaps interstellar darkness. Now we see the limitation of that framing. Coordinates assume stable reference points. Deep time dissolves reference points. The Sun will become a white dwarf. Earth will no longer be the world that launched Voyager. The Milky Way may have merged with Andromeda Galaxy. Constellations will vanish. Stellar neighborhoods will rearrange. Galactic structure will evolve. Even the observable universe will feel smaller as distant galaxies disappear beyond cosmic horizons. In such a future, asking where becomes more subtle than it first appears. Where relative to what? This question reveals the deepest lesson of our journey. Location is relational. We rarely notice this because our reference frames feel stable. On Earth, directions feel obvious. North, south, above, below. In the cosmos, such intuitions quickly fail. There is no universal up, no absolute center, no cosmic coordinate grid permanently anchored for all time. Every location gains meaning only relative to something else. Voyager taught us this repeatedly. Relative to Earth, it is unimaginably distant. Relative to the galaxy, it remains nearby. Relative to cosmic scale, it has barely moved at all. This layered truth transforms the original paradox. After 1 trillion years, Voyager II may be extraordinarily far from the Sun. It may have experienced multiple gravitational perturbations. It may have drifted through changing stellar neighborhoods. It may even have undergone rare interactions that radically altered its path. And yet in another sense, it may still remain within a familiar gravitational family, bound to a descendant of our galactic structure, still moving through matter shaped by gravity, still obeying the same physical laws. This duality matters. Change and continuity coexist. That is true not only for Voyager. It is true for the universe itself. The cosmos evolves continuously, yet its governing principles remain astonishingly stable. Gravity bends trajectories. Energy disperses. Structure forms and dissolves. Patterns emerge. Patterns fade. The same laws that governed Voyager's launch continue to govern its future. This continuity gives science its power. Even across deep uncertainty, a lawful structure remains. And yet another transformation has occurred in our perspective. Voyager no longer feels merely technological. At the start, it was easy to think of it as a spacecraft. Metal, electronics, a mission. Now it feels more like an artifact embedded in cosmic process. A tiny physical memory carried by gravity through deep time. This reframing may be the most important change of all. Voyager has become less about exploration and more about persistence. What survives? Not communication. Its signals will stop. Not mission operations. Its instruments will fail. What survives is structure. Pattern. Matter arranged intentionally by intelligence. That survival creates an extraordinary bridge between scales. Human civilization operates on centuries. Geology on millions of years. Stellar evolution on billions. Voyager links them. A human-made object crossing into timescales usually reserved for astrophysics. Very few things we build can be discussed meaningfully on such scales. Voyager can, and that gives the spacecraft symbolic power far beyond engineering. It becomes evidence of something rare in the universe, at least as far as we know. Intentional structure created by conscious beings. The Golden Record deepens this symbolism. The Voyager Golden Record does not merely store sounds and images. It stores an assumption that intelligence can communicate across space and time. That patterns may survive long enough to be recognized. That meaning might outlast makers. Whether that hope is fulfilled is unknown. The record may never be found. Voyager may never pass close to any civilization. Its message may remain unread forever. Yet unread does not mean meaningless. There is value even in preservation without audience. Because preservation changes what is possible. A message preserved can in principle be discovered. A message destroyed cannot. This brings us back to the beginning. We assume journeys require destinations. Voyager challenges that assumption. Perhaps some journeys are not defined by arrival. Perhaps they are defined by continuation. Voyager's significance may never depend on being found. Its significance may lie in the act of enduring, continuing, persisting through transformations of worlds, stars, and galaxies. And now we arrive at the final transition. We have followed the physics. We have followed the evidence. We have followed the uncertainty. Only one step remains. Not another calculation. Not another model. Reflection. Because after enough time, the question of where Voyager will be becomes inseparable from a quieter question. What does its journey say about us? There is something quietly moving about the fact that one of humanity's most enduring creations is not a monument on Earth, not a pyramid, not a library, not a city. It is a machine already beyond the planets, a silent artifact travelling through darkness. That fact feels meaningful because it contains a strange inversion of scale. Human beings are brief. Civilizations are brief. Even species may be brief. And yet from that brevity emerged something capable of crossing timescales usually reserved for stars. Voyager 2 was built by finite beings. Engineers who worked with paper schematics, early computers and instruments that now feel historical. Many of the people who designed, assembled and launched Voyager have already passed from the world. And still their creation continues outward. That continuation carries a quiet kind of immortality. Not personal immortality. Not biological immortality. Something subtler. Persistence through structure. A pattern of matter arranged by intelligence continuing long after the hands that shaped it are gone. Perhaps this is why Voyager resonates so deeply. It embodies a human contradiction. We know we are temporary, yet we create as though something might endure. We write. We build, we record music, we preserve language, we send messages. Again and again, humans resist impermanence through memory. Voyager may be one of the purest expressions of that impulse. The Golden Record attached to the spacecraft is often described as a message to extraterrestrials. In a literal sense, that is true, but perhaps its deeper meaning lies elsewhere. The record is also a message to the future, not necessarily to alien intelligence, to time itself, a declaration that for a brief moment in cosmic history on a small planet orbiting an ordinary star matter, became conscious enough to ask questions about the universe. That alone is extraordinary. Atoms forged in ancient stars assembled into molecules. Molecules organized into life. Life evolved into minds. Minds learned physics. Physics launched spacecraft. And one of those spacecraft now travels toward a future so vast that human language struggles to hold it. 1 trillion years. Pause on that number one final time. 1 trillion years ago, our universe was not even close to its current age. In fact, 1 trillion years exceeds the current age of the universe by more than 70 times. That comparison matters because it reveals how radically future-oriented our question truly was. We were never really asking about navigation. We were asking what survives cosmic time. The answer we discovered is layered. Not everything survives. Signals fade. Power ends. Civilizations may vanish. Planets change. Stars die. Galaxies merge. Yet not everything disappears at once. Structure persists. Gravity persists. Motion persists. Information can persist. For astonishingly long periods, physical history remains encoded in matter. Voyager may become one such encoded history, not eternal, but enduring beyond intuition. And still perhaps the most humbling realization is this. Even after 2 hours of following Voyager through physics, astronomy and cosmology, we do not possess a final answer. We cannot say exactly where the spacecraft will be, not because science failed, because reality is richer than simple certainty. Tiny uncertainties amplify. Gravitational encounters accumulate. Galactic evolution reshapes environments. Deep time transforms everything. Exact prediction dissolves. What remains are constraints, probabilities, and wonder. There is something beautiful about that. Human curiosity often begins with precise questions. Where, when, how far? Science sometimes answers those questions directly. Other times it reveals that the deepest insight lies not in the answer, but in understanding why certainty is impossible. Voyager taught us that. The questions seemed to demand coordinates. The journey revealed relationships. Motion relative to stars. Stars relative to galaxies. Galaxies relative to cosmic expansion. Everything connected. Nothing isolated. Even a small spacecraft cannot be understood alone. Its future depends on structures vastly larger than itself. In that sense, Voyager becomes a mirror. Its story reflects our own. We too often imagine ourselves as isolated individuals moving through life independently. yet we exist within nested systems, families, cultures, civilizations, planetary ecosystems, cosmic history. Like Voyager, our trajectories are shaped by forces far larger than ourselves, many invisible, many only partially understood, and still we move, still we ask, still we search for meaning. Perhaps that is the final gift of Voyager, not the data remarkable as it is, not even the engineering triumph. Its greatest gift may be perspective, a reminder that smallness does not diminish significance. Voyager is tiny compared with planets. Planets are tiny compared with stars. Stars are tiny compared with galaxies. Galaxies are tiny compared with the observable universe. And yet from one small world came the capacity to understand those scales. That may be among the rarest phenomena in existence. Conscious awareness of cosmic scale. A universe becoming aware of itself, however briefly. So where will Voyager 2 be in 1 trillion years? Somewhere in darkness. Somewhere within gravity. Somewhere inside a universe quieter and older than the one we know. Perhaps near a dim red dwarf. Perhaps orbiting within a merged galactic remnant. Perhaps drifting between ancient stellar neighborhoods. Perhaps somewhere no model today can predict. But perhaps that is no longer the most interesting question. Because after following Voyager across deep time, another question remains. Long after the spacecraft falls silent, long after Earth changes, long after the sun fades into a white dwarf, one mystery still lingers. If a message continues travelling through the cosmos after its creators are gone, what in the deeper sense does it mean for something to still be remembered?